Hello and welcome to a video lecture on rotational dynamics. Through this lecture we'll cover conservation of energy and conservation of momentum and how they relate to rotating bodies. Please make sure to follow along in your video notes. Make sure to look and follow along, and if you need to go back and rewind the video, do it. It's okay. And please write down any questions that you have and make sure to come in and ask them tomorrow in class. Thank you very much. Enjoy the video and have a good night. Newton's second law of motion follows that acceleration is equal to force over mass. You apply a force to some mass, it accelerates. Another way of looking at this is force equals mass times acceleration. In terms of an object rotating, we can look at this as torque is equal to moment of inertia multiplied by angular acceleration. And what this means is that these different quantities are analogous to things that we've already talked about. If I have a greater mass, then the acceleration is less. If I have a less mass, then I have more acceleration. That follows Newton's second law. The same idea holds true here for torque. If I have a greater moment of inertia, then the angular acceleration decreases. If the moment of inertia is smaller, then the angular acceleration increases for a given torque. The key thing here is that most of what we're going to talk about we've seen before in conservation of energy, Newton's second law, and conservation of momentum, as we'll get to those in a second. And the quantities are just analogous. They kind of hold that same, it's not the same value, but it's the same idea. All right. It takes work to change the energy of an object. And the same thing holds true here. It takes work to change the rotational energy. You need to apply a torque over some angular distance, change in theta in this case. And this also, once again, we'll see, depends on the moment of inertia. And this different moments of inertia will lead to different kinetic energies, different momentums, etc. going forward. As we've seen before, work is force times displacement. Here we're just looking at it as what is causing the object to rotate. So we have work is equal to torque times angular displacement. A torque provided, so it's causing some object to rotate. It produces some change in energy. This change of energy is related to how fast the object is now rotating, and therefore we can get to kinetic energy, which is now we can look at it in more of a rotational sense. Kinetic energy is 1/2 the moment of inertia times the rotational speed squared. And if we can go out, and I will show you a derivation of this in class, of how we get back to the same concepts of mv squared as we've talked about before for every object, or how we can get to the different constants for or moments of inertia, so to speak, for different objects for each thing. So these are the two similar equations that we talked about before, but now we're just adding them in a rotational sense. Everything here still follows conservation of energy. We just now have to combine the rotational and linear motion. And what I want you to really include in your notes here is to draw this picture and sketch out the velocity of what's actually happening there. So combine the arrows and everything else together to get this net motion at the end. You have a linear motion, the object here, the center of mass of the object, so that's the center of this disk or circle or sphere or whatever it is moving forward. So there's a point there and it is moving forward, in this case to the right. And also at the same time, this object is rotating, and it happens to be rotating in a clockwise manner, as we can see here, because it's rotating. The center of mass is moving forward. We're assuming it's not slipping, and it's rotating forward. So there's also some rotational speed, and it's going in a clockwise manner as you're looking at the screen. The net motion means that there is a center of mass moving forward plus a rotational aspect to it. So we would add both the translational kinetic energy, and this is due to the linear motion, and a rotational kinetic energy to get the net energy of this object, assuming the height's not changing, so they're within that. But the key thing here is it follows conservation of energy It follows the ideas that we've talked about before. We are just adding in a new aspect to the motion. Instead of just saying that the object is moving forward in a straight line, it could now be rotating, and there we have to incorporate that. This same idea holds true for momentum. Momentum is always conserved. Angular momentum is always conserved. If you decrease your moment of inertia, that means that your rotational speed must increase. Again, L for angular momentum, no idea why it's L. No idea why it was P for momentum before, but here we go anyways. L stands for angular momentum. I is representative or analogous to the mass variable that we've talked about before, and omega here is analogous to the velocity variable we were talking about before. So if I decrease the mass, the speed goes up. Here, if I decrease the moment of inertia, the rotational speed increases. So this is where you see a skater, if they bring their hands in while they're spinning, they will increase their the rate that they're spinning, increase that rotational speed. Conservation of momentum holds true. Conservation of angular momentum also holds true. So here we have a comet or some other body orbiting around the sun, and we're going to look at this in terms of conservation of energy, and then we're going to look at it in terms of conservation of rotational momentum. And we know that based on its radial distance from the sun, out here it has a much greater potential energy, and over here it's going to have a much greater, a much smaller potential energy because of conservation of energy. Out here, great potential energy, low kinetic energy. In here, small potential energy, high kinetic energy. And we see that here within the simulation, that the speed out here is smaller than the speed over here. So low potential energy, high kinetic energy, low potential energy, small potential energy, great potential energy, large potential energy, small kinetic energy. Hopefully I didn't confuse anybody going through that, just going through really quickly. We can look at this same idea within rotational momentum. Moment of inertia is dependent on mass. The mass of this object is not changing, and the radial distance squared. So here we have a great radial distance as it orbits about this axis of rotation here, and over here we have a small radial distance. So out here in this area, moment of inertia is high. In here, moment of inertia is low. So out here we're going to have a low rotational speed. In here you would have a high rotational speed. So as you bring a mass in closer to the axis of rotation for a conservation of rotational momentum, you must have an increase in angular speed or in rotational speed or angular speed. All right, for our review, I would like you to go through and compare a thin disc and a hoop of equal mass. So the key aspect here is they have an equal mass, and they also have the same radius. Make sure we include that as well. Which one has a greater moment of inertia? So go back and either look at the table in the video or open up your textbook and look at that, and just look up which one has the moment of inertia for each object. Next, for a given force, a torque, which one will have a greater change in rotational speed? And finally, we looked at an idea earlier about rotational work and energy, that it follows conservation of energy. Assume both are rolled down a slope without slipping, the hoop and the disc. Which reaches the bottom first? Which one will have a greater linear speed? Think about this in terms of the moment of inertia. Please make sure to write down any questions that you have, and we'll come into class and go over them tomorrow. Thank you very much, and have a good day.